In this video, we'll talk about how to test whether a logical argument is valid. So our goal is just that. We want to determine whether logical arguments, are valid or invalid. All right, so I want to look at an example which says, if it doesn't rain, I will go for a run. When I run, I take a nap. Therefore, if it doesn't rain, then I will take a nap. So first I want to introduce some terminology. So the stuff that ultimately I am trying to determine whether it happens or not, in this case that's everything that comes after the word therefore. This is called the conclusion of the argument. I'm trying to conclude that if it doesn't rain, then I will take a nap. And the stuff that comes before that, all of this, I'm going to refer to this as the givens. Or sometimes we call these, in logic, the premises. But usually I'll just call them the givens. So I'm given this stuff at the top in green, and my conclusion is this stuff down in blue. Alrighty, so I want a systematic way to determine whether this argument is valid or invalid, and we're going to use logic for that. Although, after reading this on an intuitive level, hopefully you might see that, oh, it seems like this is a true statement. Alrighty, so what I'm going to do is I'm going to label some of the propositions that show up here. So I'm going to let R be the proposition that it doesn't rain. It doesn't rain. And let's let G be the proposition that I will go for a run. I will go for a run. So the very first sentence seems like an if-then statement. Okay, and then there's this matter of taking a nap. I'll call it N. N is going to be I will take a nap. I will take a nap. So now let's write down this argument in logic. The argument in logic. And the reason we do this, instead of just trying to look at it in English and try to determine whether it's valid or not, is converting it to logical form gives us very defined rules that we can use to determine validity or not. Whereas in English, sometimes the wording can be a bit ambiguous. So converting to logic removes that ambiguity. Alrighty, so the structure of our argument is, the very first sentence is, if it doesn't rain, then I will go for a run. Which is, if R happens, then G happens. The next sentence says, when I run, then I will take a nap. So that's if G happens, then N happens. So I'm going to write that underneath it. So we have these two givens. And then I'm going to put a line. And then underneath that, I'm going to put a symbol, 3 dots. This is a mathematical symbol for therefore. These 3 dots mean therefore. And then my conclusion is, if it doesn't rain, then I will take a nap. Which is, if R happens, then N happens. So R implies N. Okay, so just reading this whole argument is saying that if R happens, then G happens. And if G happens, then N happens. So therefore, on an intuitive level, it seems like, okay, if R happens, then N is happening. So to verify this, I need to check. If R implies G and G implies N, if those two given propositions collectively imply that R implies N. So let's translate this into more of a logical thing that I can check. So in other words, I need R implies G, and let's convert the and to a symbol, and G implies N. Let's put this whole thing in a big parentheses. These things need to imply, so let's put the symbol for imply, arrow. They need to imply that R implies N. this whole thing, we need this to always be true. And if it's always true, that means this argument is a valid argument. So how can I check if some proposition is always true? Well, we can check it with a truth table. So check this with a truth table, and that is what we are going to do next. All right, so let's start our truth table. So we have these three kind of basic propositions that we're starting it off, R, G, and N. And then we have a bunch of implications. So we have R implies G. We will have G implies N. We also have R implies N. Start to put a horizontal line here. I'll put these double vertical lines that separate kind of the building block propositions from the ones that we get after that. Okay, so then I also have R implies G and G implies N. And then finally, we have R implies G and G implies N. If that whole thing implies R implies N, I need to give myself more room here. Alrighty, so just shifting over my truth table a little bit so I can fit in that R implies N. Okay, so now let's draw in some vertical lines to separate these columns. Okay, so now let's build a truth table. So starting with N, I'm going to alternate true falses. True false, true false, true false, true false. And G double trues, double falses alternate. Double false, then double true, then double false. Okay, and then R, 4 trues and then 4 falses. 4 trues, 4 falses. Alrighty, so now let's fill in the truth table values for R implies G. Okay, so R implies G, and the implication is only false when the first part is true and the second part is false. So that happens in the third row and in the fourth row, where R is true and G is false. So here it's going to be false. But in all other situations, that implication is going to be true. So it's true when both R and G are true. And it's also automatically true when R is false. Okay, so now let's do G implies N. This one's going to be really similar. The only way for it to be false is if G is true and N is false. So that happens in the second row. And it happens, in this sixth row. So it happens down there. And then that's it. So the rest of these are going to be true. Let me start to write these trues in gray. Alrighty. Now let's do R implies N. Same deal. For this to be false, I need R to be true, but N to be false. So that happens in row 2. And it happens in row 4. And that's it. Those are the only times where R is true and N is false. So the rest of these would be trues. So trues. Alrighty, so now we have to form this conjunction, this AND statement involving the R implies G column and the G implies N column. So an AND statement is true only when both of the pieces are true. So that happens in this first row. In the first row, it's going to be true. Where else would it happen? Okay, it happens down here, 2 trues. And then the last 2 rows. We get some trues there, but the rest of these should be falses. So this should be false, 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 false. Alrighty, so we are on to the last column. So the last column, we have this implication that we're forming, where the first part of the implication is this previous column, R implies G and G implies N. Okay, and the conclusion is the R implies N column. So when the first part of an implication is false, the whole implication is going to be true. So that definitely happens in this row, because the first part of the implication is false. So similarly here, it's going to be true. Here it's going to be true. Oops. Here it's going to be true. And then here it's going to be true. And then in the other rows, we have true implies true, True implies true, true implies true, true implies true. And that makes an implication true as well. In other words, I never have a situation here where the first part of this implication is true, but the second part is false, because that's the only thing that can make the whole implication false. Alrighty, so we are ready for our conclusion. Since R implies G and G implies N, since that implies R implies N, since this proposition is always true, this means that the argument is valid. So next I want to state this method kind of in general of checking whether an argument is valid. So in general, if I am given propositions P1, P2 up until Pk, so if these are all of the given propositions, so the example we just did, there were 2 given propositions, but sometimes there might be more. And then we have some concluding proposition, which I'm calling Q. So a concluding proposition. This argument is valid if we form the proposition P1 and P2 and ... and up until Pk, if that implies Q is always true. And remember, the terminology for something always being true is, i.e., it is called a tautology. And that's what happened in the example we just did above. These truth values were always true at the end, which made this proposition a tautology, and that's how we knew the argument was valid. So, looking back to our argument here, we said earlier that it seemed like this was sort of intuitively true. And going through the whole truth table process seems like a lot of work. It seems like it might even be overkill for something that, seems like it's intuitively true. But this is of importance to us in logic, mathematical logic, because we want to have a way to verify that even the things that we take for granted that seem like they're obviously true are in fact based in logical facts and logical truths. That's important to showing that mathematical concepts and logical statements are sound.